Double click on the session 1 script, it should automatically open up in RStudio. Now there are 4 sections of RStudio. On the top left you have the editor screen, and this, as you can see, is where we write the script. Below that we have the console, and this is where the script is run. Top right we have an area which we'll ignore for now but come back to at a later point. And bottom right, this area contains a couple of windows that are worth pointing out now. Firstly, the plots window. So when you create a plot or a graph in the editor screen, it will be shown in this area here. And also a help window. So if you're looking for help with a function or a package that you're trying to use, you can write a line of code over here and it will open up a help window here that will give you some information, for example, about what the package, what arguments the package needs included in it. But we'll come back to that. So you can navigate, so you'll notice that the headings and subheadings in the script have got 4 hashtags before and after them. And this is useful because you can actually navigate your way through the script based on those headings and subheadings. And obviously the longer the script, the more useful this is. Okay, so we're going to start by setting the working directory. And to do that, we go to Session and Set Working Directory and choose Directory. So mine's already set to the correct one, but if I just come back to my desktop, so we go to Desktop in my case, where are we? Our practice folder, CMRG, and you'll notice when you select it, the files in there will be greyed out. You can't select those, but that's fine because we're just selecting the file. Now the working directory is where I will look for files that you're trying to upload, but also for where you will save plots and save scripts, etc. So it's really important that at the beginning of each session that you set the correct working directory. Okay, moving on. So we're going to start by looking at different types of data in R. Now, there are a few different types of data, and we'll go through them sequentially. Firstly, string data or character data, and that comprises characters that are contained within double quotation marks. For example, CMRG. And what we're going to do here is assign this variable, CMRG, to something called an object called string. And to do that, very simply, we just put an arrow in between them. So if we select this line, and if you're using a Mac, press Command Enter, or if you're using Windows, Control Enter, and you'll see if you come down to the console window here, it tells you that it's executed that command. So nothing actually printed at the moment. All it's saying is that it's assigned CMRG to an object called string. Now we can subsequently actually look to see what this object contains, and we can do that by printing it to the console. And there's a couple of ways to do that. Firstly, you can use the print command. So if you go to line 16, it's print with the name surrounded by brackets or parentheses. And if we go onto that line and run that line, you'll see down in the console it's telling us that the object string contains something called CMRG. Now actually there's an easier way of printing something to the console. We don't actually have to use the print command. We can just name we can type the name of the object we're interested in this case string, run that line, and we get the same answer, CMRG. So we might be interested to understand what class of data is contained within an object. And to do that, we can use the class command. So that's just class with the name of the object contained within parentheses. Now if we run that line, we're told that the string object contains a variable or contains variables that are of the character nature. And we know that to be true because we've just assigned CMRG to it. Now whole numbers or decimals are stored in R as numeric data. Now, if we want to store data as an integer, then you've got to add the letter L afterwards. And let's just demonstrate that. So let's assign the number 1 to an object called x. And then we're going to ask R whether the object x is an integer. And we do that by the is.integer and then the object name, in this case x, within parentheses. So let's run that. And we see in the console that this is false. And of course, that marries up with what we were saying before. So if we do the same again, we repeat that, but we add an L after the 1. Is x now an integer? And we're told in the console that yes, that's true. So the difference between numeric and integer data relates to how they are stored. And for now, it's not particularly important. It may become so at a later point, but we won't dwell on that for now. So we can combine data into something called a vector. And to combine data, we use the combine function, and that simply is a C with parentheses. So here we're going to combine the data 1, 2, 3, 4, and 5. And we're going to assign that to an object called x. So let's run that, and in the console it's going to tell us there are no errors. It's run that, and that appears to be successful. Alternatively, we could just, to save time, do 1 through x with a colon, again using the C function, so we'd get the same answer there. Now, to demonstrate what logical data is, we're going to use the object x that we've just created. So we're going to ask R whether there are any variables in the factor x that are equal to 4. So to do that, we're going to do x, and notice here we've got a double equal sign, and that essentially is equals to 4. So if we run this, we'll get false, 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 true, false, and that marries up with what we obviously know here, that 1 isn't 4, 2 isn't 4, 3 isn't 4, 4 is 4, 5 isn't 4. So this is an example of logical data. Is something true or false? And let's try another couple of examples. So in this case, are the variables in the factor x less than 6? And if we run that, we get true, 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 because all of these are less than 6. And then finally, are the variables in the factor x greater than 3? False, 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 true, true. And this makes sense from what we know we've entered into the object called x. Now, for the moment, I wouldn't dwell on different classes of data. We'll come on to that, and that does become important. But one of the nice features about R is that when we upload data, say from Excel, it will automatically at least attempt to detect what sort of data it is and assign a category to it. Now, sometimes that will be incorrect, and we'll come on to address that. Yes, so it's not something we need to worry too much about, but we can change it if needed. Okay, so we're going to move on to task 1. So the best way to do this, I think, is I will keep so I've got the answer below here, but I'll only scroll up to the instructions. I'll read this out, and then it's probably best just to pause the script, have a go at seeing if you can do it yourself, and then I'll scroll down and show the answer. So based on what we've done so far, I'd like you to create a vector containing the following: Damien, Vicky, James, Kat, Jack, Tony, Kirsten and Steph, and assign it to a factor called Tyler group. And sorry, can't quite see the end of there. There we go. So we're going to take these names, which will create a vector, and assign it to something called the Tyler group, just as we've done with, the numbers up here. And then I would like you to print the Tyler group to the console being down here, and then check the class of the data contained within the Tyler group, and remember that we used the class command up here to do that. Okay, so if you have a go of that, and as I say, it may be best just to pause here as I'll proceed then to show the answer. Okay, so you should have something like this. So because this is string data, we're putting quotation marks around it, and R recognizes that by changing it to green. We're using the combine function, so C with parentheses, and we're separating each of the variables that we're entering by a comma. And then we have our arrow that's telling R to assign it to something called an object called Tyler_group. An important point here is that we can't have spaces in names, in object data frame names, in any names. So it's good to be consistent with how you deal with that. I tend to use an underscore, but a full stop, whatever works for you and will be memorable for you, but be consistent with it throughout. So if we run this line of code, again on Mac this is Command Enter, on Windows Control Enter, then we can see down here that the console is happy with what we've done. If it didn't like it, it would come up with a red warning message, which is something that we'll become quite familiar with. And then we want to print this. We're not going to worry about the print function. We're just going to type the name, Command Enter, and there we go. So it's telling us that the Tyler group object we've created contains Damien, Vicky, James, Kat, Jack, Tony, Kirsten, and Steph. And now we want to inquire about what sort of data is contained, what class of data is contained within the Tyler group. So let's run that, and we get that it's character data, and this fits in with what we know to be true. Okay, so moving on. So we've covered vectors, we've covered different types of data, and now we're going to cover something called a data frame. So when we talk about data frames, and there are lots of different names given to various types of data within R, and it's useful to know these, but it's not imperative. Just if in doubt, call something an object. But a data frame is essentially a table, and it can contain numeric, factor, or character type data. So we're going to do another exercise now. So we're going to use the factor we've just created, the Tyler group, and we're going to combine it with another one which we're about to create to make a data frame. And this will hopefully become clear. Okay, so task 1.2. Again, so if I talk through this, and then if you pause, have a go yourself, and then I'll show you the answer. So create another factor called gender. Include the correct gender for each of the members of the Tyler group. And then print this to the console and check the class of data within gender. So you're repeating what you've done before, but you're assigning a correct gender to each of the members of the Tyler group. You're going to print that and then check the class of data. Okay, so if you pause now. Okay, so this is the answer. So we've got the correct genders for each of the members, and that is being combined using the combine function, and again separated by commas, and of course, because this is character data or string data, we have quotation marks around each. It's being assigned to a new factor called gender. So if we run this and then we print gender, and we see male, female, male, female, male, male, female, female, and then we can investigate the class of gender, and of course it tells us that it's character. Okay, so what we're now going to do is combine these two factors, the Tyler group and the gender factor, and we're going to mash them together into a table. And we do this using the data frame command. So an important point here, you don't need to memorize how particular ways of doing this, or you don't need to memorize the code for creating a data frame. You know, over time I think that will become intuitive, but my experience is most of the battle is knowing what to Google and then being able to interpret what you find in Google. So if you're not sure how to do something, there will be tons of information online about how to do it, and a lot of it is very accessible, including really well-structured examples. So it's just a case of knowing what you want to do, getting the right search term, and then executing from there. But here we're going to use the data.frame function, which does as it says. So we've got data.frame parentheses, and in those parentheses we've got the first column that we're going to create, which is the Tyler group, and a comma to separate, and the second column, which is gender. And then we're going to assign that using our arrow to a new object name or data frame called Tyler gender. So let's run that and print that, and we see down here in the console now we have a new table, Tyler group, names, and gender for each. Okay, so a couple of reminders here to be consistent. I think I've mentioned most of this, but R is case sensitive. Now I've made the mistake actually throughout this script that sometimes I've capitalized the first letter of a variable name and other times I haven't, and this can really catch you out at a later point. It's a really common source of error in your code, so probably best just to keep everything lowercase. And what other things have we got here? So consistent naming format, make things memorable and meaningful, and of course no spaces are allowed. So instead of a space I use an underscore, but you could use, well, you could use anything as long as it makes sense to you. Now obviously if we had a data set and that could include numerous variables, doing this each time would it be incredibly tedious and probably not very efficient. So the good news is we don't need to create data frames from scratch. Rather, I think the best way to do it is to import your or collect your data and sort your data in Excel and then import from there. And that's what we're going to move on to do now. So importing data and checking the data. So there's a note on here to switch to PowerPoint. I won't do that here, but what I will do is attach a PDF that just has a few pointers about actually, let's see if I can do it. There we go. Yeah, let's do that. So let's just make that full size. Oh, there we go. Wrong button. There we go. So this is the data frame that we're going to be working with, or the data set that we're going to be working with, and I'll go on to explain what this fictional experiment was. But a couple of things to point out, because if you set your data up incorrectly in Excel, then you're going to have problems once you import it into R. And I'm going to reiterate, and it's probably worth doing some of the key points around formatting. So as I said before, no spaces, be consistent. Do not start with a number, so don't have a name, a variable name here, say 60-minute glucose levels or something like that. They obviously have to be unique and case sensitive. As I say, I think it's best to keep everything lowercase, but it doesn't matter as long as you know what you're doing and are consistent with it. So you can't have blanks in your data set. That will confuse R. Now you can, if you import data with blanks, it's not a major problem because you can retrospectively fix that in R, but I think the best approach is just to replace all blanks with NAs. And you'll see here the reason we've got NAs is because this is body mass. So we've got 4 different levels of time, so four measurements based on time, and those being 0 minutes, 30 minutes, 60 minutes, and 90 minutes. Body mass was only measured at baseline, so there are no values for these. So we put an NA in there and we can deal with that in R without a problem. And also if there are any special formatting features that you've used, for example, comments and such like, then make sure they're deleted beforehand. Okay. All right, where were we? Okay, so importing and checking the data. Here we go. So we've already set our working directory, and we can access the data that we've already saved. So it's an important point if you're looking at this, that you need to have saved the example data set, in this case as a .csv file, into the correct folder. And if you don't, let me give you an example. If I change the working directory, and let's say I just change it to desktop and press open. So you see down here it's saying set working directory desktop. Now if I run this, it's going to look for this file called example_data_set.csv in desktop, and that's the red error message we get down here saying that it cannot find that, and that's reasonable because it doesn't exist in that folder. But if I now change the working directory to the correct one, where are we? Okay, so CMRG, and now it's changed the working directory. There is a file in there called that, and now it's happy. Okay, so the other thing to note is, so we've used the read.csv. You could do this as an Excel. I believe there are reasons why it's good to convert the data to a CSV file beforehand, but I can't recall what those are, so it might be something to look up. But as I say, you can just take an Excel file and import it. But what we've done here is read, or read even, the example data set, and now we've assigned that to an object called ketone. So ketone is the name of the data frame that we're going to be working with, and we'll be working with that over all 3 sessions now, so we'll get familiar with that. Okay, so we might, once we've imported the data, probably the first step is to make sure that it looks okay, that it sort of makes sense, nothing funny has happened as it's been imported. And there's a few different ways of doing that. Maybe the best starting point is to look at the structure of the data frame. And this might be important because actually we might be getting data from someone else. We may not have even conducted the experiment. So we want to get a feel for what this data is. So if we use the structure command, and that's just simply str with parentheses and the data frame name in between, and run that, and you see down here that we get a lot of information about what's contained. So we've got 80 observations of 8 variables, and those variables are listed, and it gives you some example of the data that's actually contained in each variable, and importantly it also tells you the class of data that R has decided this is. And generally speaking, this is probably right. Not always, and we'll sort of come back to this at a later point. But initially, if we just take the top line, it's decided that the participant ID is an integer, and this isn't the case. It's nominal data. Now, in reality, it probably doesn't matter, or it almost certainly doesn't matter for analysis purposes, because we're not going to be analysing or using participant ID number. And in fact, we could have left that out of our import, but as it's here, let's use it to practice changing data types. So we've got this data frame, but what happens if we want to change the class of data within a particular variable? In this case, we want to change ID from integer and convert it to a factor variable, which is something that we created when we were generating these for the Tyler group. This would be classed, gender would be classed as a factor variable. So essentially, here we've assigned a vector to a factor, and that's similar here. So these are now considered to be factors, but I wouldn't dwell on that too much. So here's the code to do that, and I should say that there are multiple ways of doing this. This is just a way, and if you went online and typed in changing factor class within a data frame, there'd be pages and pages of examples of how to do that, both on Google and on YouTube, etc. And yeah, there are multiple ways of doing this. This is just one way. And if we break this code down, so let's start from the right-hand side and work to the left. So we've got this part here which says ketone, and we've got a $sign and ID. And what this is saying is that the ketone is the data frame, and the $sign is telling us which variable within, or that we want to use a variable within the ketone data frame. And if you notice down here, all of these have $signs in front of them, so that gives you a clue as to what we're doing here. So ketone data frame $ID. Now currently it's as an integer. However, what we want to do is turn it into a factor, and then we want to, once we've turned it to a factor, we want to assign it to back to ketone ID. So we're taking ketone ID, which is currently an integer. We want to assign it to a factor. We want to make it a factor and then reassign it to ketone ID, which I appreciate is a little bit maybe complicated, but it's maybe the best way to do this is actually run the code. So notice here we've got integer. We'll run this line, and that's all worked okay. And then if we do the structure command again, now we have factor. Okay, so it's taken, it's not changed any of the variables, etc. It's just changed how the data is recognized within the data frame. Okay, so task 1.3. So we might want to, so there's a command called head, which then will display the first 6 levels or observations, sorry, of the data frame. And this is quite useful, particularly if you've got a really large data set which has got thousands of entries. You don't want to print the whole thing because it would overwhelm the console. So just to get a grasp of the sort of data that's contained, the head function is quite useful. Now we haven't actually covered how to do that yet, but I think intuitively you could probably guess based on, for example, the structure command here. So if you use that as a model, then have a go at running the head function to identify or show the first 6 observations within the ketone data frame. Okay, so you should have, quite simply, head in brackets or parentheses ketone. And if we run that, there we go. We see the first 6 entries for the ketone data frame, and this gives us some useful information. We can see, for example, body mass has some NAs, and we can see there are different levels of time, genders, and we can see that beta hydroxybutyrate, glucose, and NEFA have all been measured at each of these levels. Notably also, you see the difference here that in theory, we could have just had NAs here for male. You know, we could have just assigned their gender at baseline and not repeated that. But again, it doesn't actually, as we'll come on to see, because we might want to segregate gender, some of these numbers, some of the independent variables here, for example, NEFA and glucose, the results based on gender, it's actually quite important that we have male assigned to each level of time, and hopefully that becomes clearer as we go along. However, that's not the case for body mass, because we're not going to be doing any comparisons based on body mass. Okay, so where are we? So yeah, just the point that this is, we've only got 80 observations in this data frame, so it's pretty small. So actually, in this case, it might be best just to print the whole thing, which we already know how to do. So there we go. We've got the entire data frame there, and that all looks as I might expect. But there is another way of doing this, and if we go up to this top right-hand window that we mentioned before, you'll notice as we've been going along, the vectors that we've been creating, and here the data frames we've been creating, so the Tyler gender and also the ketone data frame have been stored up here in the environment tab. So if we select the ketone tab, there we go. So we can get a view in the editor window of the entire data frame. And that's a good sanity check, particularly if you know, well, no, either way, if you just want to just have a look and get a feel for what the data contains, then this is a useful way of doing it. Note that we can't actually edit anything in here, so this is just a view only. So let's go back to our script. So moving on, the next stage is installing and accessing packages. And this is really, in my view, the key selling point for using R versus Prism or any other or SPSS, etc., is the flexibility you're afforded by using different or being able to download various packages. And a package is simply a piece of software, because R is open source. Then people can write their own packages to perform specific functions or look at specific types of data and upload it and make it freely available for people. And this just massively increases the way that you can look at data and think about data and analyze data that you may have. So to install a package, it's very simple. You just use the install packages function, and actually to uninstall packages, it's the uninstall.packages function. So in this case, we're going to install a package called ggplot2, which we'll come on to use and is a really useful package for visualizing your data. And so we just put that within quotation marks. Let's run that line. In this case, because I've already got it loaded, it's going to ask me if I were to restart. I don't think that's the case if you're doing it from new, but I'm not going to at this point. And down here we can see it's contacting the central store for all the packages, which is called CRAN, and it's downloaded. So that's worked successfully. And you can see they're fairly 3.9. This is a big package, and it's only 3.9 megabytes, so it's pretty small and won't take up a huge amount of memory. Now, you only need to install packages once, with a slight caveat. Every time you update RStudio, you do then need to reinstall packages, which is a bit of a pain, but every time you open R for a new session, you do need to load the packages again from your library. There are a couple of ways of doing that, but the best way, particularly if you are going to be sharing your script, is to use the library function. And this is as simple as you probably think. You just use library and then include the package with quotation marks around it. So if we run that, this is now selected. Now you can double check this, so this is the other way of doing it, which isn't necessarily recommended, but this is your packages screen. And if we look now for ggplot2, we can see that that has indeed been uploaded or been accessed from our library. Okay, so we're going to we're going to install here several packages that we'll be using. Many of which may already be selected, but let's just run all of these. So if we select all of them and do Command Enter, then it will do them all in one go. I'm going to get lots of messages up here asking if I want to restart. Hopefully you don't get that. I'll say no to all of these. And as we can see, it's loading and installing those. Okay, good. No errors. Right, so task 4, 1.4, is another package that we'll need at a later point, is the emeans package. So I'd like you to install, so copy this, but do it for emeans. Okay, so it should look like this. Let's run that. Okay, it looks like it's worked, so we can commence. Oh, it's still going. Well, we'll let that carry on working. So, so there are thousands of packages available, and you can get a full list here. Let's new window, and if we go back to this. Okay, so this is a full packet, full list of packages that you can access, and I mean there are thousands. We're still in the A's, so you get a sense of what is possible here, perhaps. I mean, this seems a little bit overwhelming, and clearly you wouldn't want to just go through this and try and look at the names of each package, but maybe a better way of doing it is to think of a particular need that you've got. So an example is that comes to mind is the continuous glucose monitors. So these are monitors that, as the name suggests, continuously monitor your blood glucose levels, or at least provide an estimate for that. And that provides a huge amount of data, 24 hours of data, say for 2 weeks for each person, and that's a sort of mind-boggling amount of data that you maybe need to get your head around. And the way the approach to doing that is not necessarily obvious, and certainly I don't think it's possible to do it in a very good way within Prism or Prism or SPSS. So let's just type in continuous blood glucose . Okay, so continuous blood glucose monitor package in R, and first thing we come up with, so this is actually a paper about a package called CGM analysis, so continuous glucose monitor analysis. So you can see that if you wanted to write, I mean, the data you can get from continuous glucose monitors is amazing, but obviously it's only as good as your ability to actually analyze it. So you can see someone's actually gone to the trouble of doing that, or creating a package to do that. And as I sort of said before, I stress again that I think this is the real benefit of using R, the flexibility you have. Okay, moving back. So I guess the task here is, if there's something specific to your work that maybe you think there could be a better way of analysing, then it's worth having a search online and seeing if someone has created a package that might be useful for you in your work. Okay, so a brief explanation, because we're going to go on to actually analyze this data set that we've uploaded, the ketone data set. So this is a fictional experiment that was run to determine whether consuming a ketone drink lowers blood glucose and non-esterified fatty acids. And there were 10 participants that were recruited to a match group design, random order controlled study. And a baseline blood sample was taken at 0 minutes, and then participants consumed a ketone containing drink. And then further blood measurements were taken at 30, 60 and 90 minutes while they rested. So let's just have a look at the ketone data frame again. In fact, it's probably best just to look up here. So we can see that within this experiment, we've got so we've got condition and 2 factors of condition and time. And condition has 2 levels, so ketone and control. And time, which has 4 levels, so 0, which is baseline, 30 minutes, 60 minutes and 90 minutes. And then we've got a few variables that we're interested in comparing, so glucose and NEFA that have been measured at each level of time. Okay. Right, so initial data exploration. So we've got the data into R, and we've checked that it all looks normal, and we've uploaded some packages to help us assess this data. And actually, predominantly, we're going to be using something called the DPLYR package, DPLYR. Now you can, I mentioned earlier that you can get help with a particular package, and to do that, you just need to put a question mark before it. And okay, so unfortunately that isn't working for some reason here, but anyway, hopefully it works for your screen. But possibly anyway, the better approach to finding help with the package is to Google. Okay, so our goal here is that we want to provide or create a summary table that gives us a summary of the mean and standard deviation for 3 variables, beta hydroxybutyrate or BHB, glucose and NEFA. And let's break. So this is a a relatively long line of code, but we'll break it down. You'll see how simple it is. So firstly, we've got the name of our data frame here, which is ketone, and this item here is called a pipe. And what this does is tell us that everything after this pipe applies to what was before it. So in this case, everything after applies to the data frame called ketone. And what this means is, earlier on I introduced the idea of this dollar sign. And if we didn't use this pipe, if we took out this line of code, that line of code, and just had from summarize onwards, for each of these we'd have to write ketone, dollar sign, and the same here, ketone, dollar sign, so on and so forth, which is a bit of a pain. So to prevent that, if we just include this dollar sign, and automatically it knows that, okay, all of this relates to the ketone data frame. Now we're using the summarize function, which does as it says, it creates a summary table in this case of everything that we put in brackets here. And you'll see that what we're doing is creating a variable called bhb_mean, and that equals the mean value for bhb. So the mean value for, as I scroll up in the console, it'll be the mean for bhb. And we're doing that and then we repeat that for standard deviation for bhb, and that just continues with the other variables we're interested in. So let's run that. And you'll see down here in the console that we get exactly what we were after. So we've got a table here. So BHB mean, BHB SD, glucose mean, glucose SD, NEFA mean. Actually, for some reason, it's missing off the SD. Oh, there we go. So we've got an error here because I've repeated the name twice. So you see there, we've got a variable called NEFA mean and a copying error because I've just called this one NEFA mean as well, but this should be NEFA SD. And now let's run that again. There we go. So we've got the NEFA SD column in there. Okay, so I think we've covered most of this. So the next task is to create a summary table from the ketone dataset for body mass showing mean body mass, or let me rephrase that. So in the ketone dataset, we've recorded people's body mass at baseline, and I want you to repeat what we've done up here, but create a variable called BM mean, so body mass mean, and that will equal the mean of body mass, and another variable called BMSD, and that will that will equal the standard deviation of the participant's body mass. So I'll give you a second to do that. If you pause your screen. Okay, so you probably, if you did this, well, correctly is the wrong way, but if you followed what we've done up here, you will get an answer that will say NA. Now, why is this? So if I run what I think you probably entered as your code, and there we go, we get NAs down there. Now that is because if you remember, if let's go back to our data frame here, you'll see that body mass was only measured at time point 0, so at baseline. So we've got a number of NA values in there, and what it's currently trying to do is take the average including the NA, and obviously you cannot take an average of a string variable called NA, so it's reporting this is not applicable, and quite right too. So what we need to do is use the na.rm equals true, and what this translates to is NA removed equals true. And so we can exclude the NAs before doing mean and standard deviation sums. So the code would then look like this. So pretty much the same. It's just that after the body mass, there we go, after body mass we do na.rm equals true and na.rm equals true there. And now if we run this, there we go. We've got a sensible value. So 69.93 and 18.0. Okay, so moving on. We're nearly there for this session. Filtering. So filtering, as it sounds, is maybe in this case we're interested in looking at values, means, and standard deviations for subsets of this data, rather than currently we're looking for the mean of the entire BHP column. And obviously that's not particularly relevant to us because we've got two different conditions here. So we might want to use some filtering to separate or to distinguish between, for example, control or the ketone group. So let's scroll down. So we say here, let's remind ourselves what's in the ketone data. Well, we just did that, but there we go. And it's useful to do this just before you set about doing tasks or any writing of the code, because you sort of, particularly because you need to know what the correct names are for the variable names, and making sure that you're putting capitals in the right place, etc. So the task here is, how do we filter data using the Deepler package? So really the task is just to try and practice. You've got something that you want to do, a function that you want to do. You don't currently know necessarily how to do it, and you need to search in Google to find out. And this is actually, I think, one of the most important skills, being able to filter, excuse the pun, through the search responses to find out what you want. So I'd encourage you just to have a quick search, probably, if it's consistent with what I've done before, the top result that you'll get. In fact, let's give it a go. Filtering data in Deepler, select that, copy it, and enter here. Okay, so let's go for the top response. I think this is the one I found. So this gives you some information about the Deepler package. So there's some information up here, the arguments that it contains, i.e. what you've got to enter. Let's see if we can scan down, and here we go, examples. So this is, I think, the really useful thing, is that they provide examples of how to use it. And in this case, filtering by one criterion, and this is a Star Wars database, and so you can see the data frame here. And they want to filter by human. Okay, I can't actually see where human is there. Okay, well, it's not obvious to me where it is, but you can see the function. So let's go into this code. So they've got filter, Star Wars is the name of the data frame, comma, and then species. Sorry, that's what we're looking for. So there should be a variable in here called species, and I still can't find that, but it might just be off screen. So they want to filter out species, so this is equal to humans, so we only want the human species. So let's go back to our RStudio. So we're through there. So here we go. Let's apply that now to our code. So with this knowledge, let's repeat the code above, but include a filter to show only the ketone data. So let's go through this step by step. Ketone. So this is the data frame. We've got our pipe. So everything that follows, oops, let's undo that. Everything that follows applies to this. Filter. So think what we just seen. So we've got filter, we've got condition equals. Now notice we don't need to put the data frame in here now because we've got this pipe. So it automatically knows that this relates to ketone, whereas before in the Star Wars example they put the name of the data frame there. But here we just write ketone is equal to, and condition is equal to ketone. And notice we put quotation marks around this because it's a string data or variable. Now we also need to apply a filter here, a pipe here, because again everything after this applies to this filter. So we're only going to be showing a summary table for the ketone group only. So let's run this and hopefully this makes a little bit more sense. Here we go. So this is now, I mean, we could contrast this. So if you see the values down here. This should only be for the ketone group, and looking at it, I'm almost certain that is the case, because you can see that the mean ketone level is 1.76, and I suspect that wouldn't have been the case. But let's just scroll up. There we go. So this was the original one, and you can see that just based on the ketone level, we can see that, yes, something has changed here. Okay, so that seems to have worked. So next task is now simply repeat this, but do it for the control group. Okay, so hopefully you've had a chance to pause and have a look at doing that, and hopefully you found that one quite easy, because it's just a case of replacing this with control, and this would be the code. Right, so let's run this. And yeah, there we can see that makes a lot of sense. So we can compare, but it's not particularly easy to do so, I have to say. I mean, we can certainly see that there are differences there, but that's maybe not the best way of doing this. And also doing this separately would be pretty tedious, and of course, you know, inevitably that's not what we have to do. There are much more intelligent and better ways of doing this. And again, I'll just re-emphasize that the way I'm going around this is not the only way, it's a way, and you might find as you get more experience that there are many better ways of doing this, which I'm sure there are. Okay, so we're going to create a single line of code to give us a summary table based on ketone or based on condition, so separated out by ketone and condition. I hope that makes sense. And again, we're going to be using the deepler package to do this, because we're going to introduce another function that's called group by. So all of these, so the pipe, the group by, and the summarize are all features of the deepler package that make it far easier to filter and work with data frames. So ketone, pipe, and now we've got group by. And this does as it says, it groups by condition. So instead of filtering, we're grouping, i.e. presenting the data for each condition separately. The other thing that we're going to do here is an add. So we've got, otherwise we've got the summarize function, which is as above. And also I've included at the end here just a variable that's going to be called n, which will tell us the number of observations at each level. So it's a good way of checking to see if there's any missing data, just having a quick glance on that. So let's run that. There we go. So that's much easier to compare now, and we can make some direct comparisons. So we can see clearly beta hydroxybutyrate is much higher in the ketone group, but also you can see here. So these are the variables that we're interested in. The question is, does ketone ingestion lower glucose and NEFA? And I mean, it certainly seems to be the case. Certainly so for NEFA, and it's sort of based on the standard deviation and the mean there, we might expect that could also be the case for glucose, although it's not quite as apparent there. Okay, so task 1.9, now let's try filtering out baseline values and repeating the grouped summary. So this clearly isn't something that I would necessarily do in practice, you know, to filter out baseline values, but for the sake of demonstration, let's give it a go. So actually we've got some code here, and I'd like you to try and work out where there's two errors there, and they come before this. So this is all fine, summarize onwards, but there are two errors in this section, and I'd like you. So if we try and run this now, let's have a go. We get lots of red warnings, and you can somewhat figure out what might be happening there. There's some clues in there, but it's not very explicit. So that's one drawback of this, of using RIFound, is that you do have to sort of think it through for yourself a little bit. But I'll give you a second if you want to pause, and then I'll show you what I think are the errors. Okay, so first things first, we are missing a pipe here. So we've got a pipe of the group by condition and after the ketone, but we haven't put a pipe in after the filter. So the code is kind of broken at that point. So let's add a pipe. Oops. Okay, and I mean, we do know that there are 2 errors here, but let's just try running that. Okay, still no luck. So, okay, so I'm just looking at the error message here. Again, it's not particularly useful. So one of the big things that I mentioned before is about capitalization, and you notice here that condition has got a capital C, time hasn't, and I suspect if we then just quickly check the ketone data frame, okay, we can see that time is capitalized, so that's an error. And now if we run it again, there we go, it works. Okay, so this is now filtering out all the baseline values. Just to re-emphasize, this isn't particularly useful for actual analysis, but it gives us a way to demonstrate some of the features and functions, etc. Okay, let's remove that. So that is then the end of the session. So save progress. So you go File, Save As, and then you can save from there. So yeah. And the other thing that's worth doing is clearing up after your session, because if particularly if you don't close down RStudio, then some of these things can be or are stored in memory. So to try and to clear everything away, so to clear the console, if you do select it and then press Control L, that will clear that. If you do have any plots, you can we haven't, but you can get rid of them with this, and equally. You can use the broom to get rid of these saved variables. Are you sure you want to remove all of the objects in the environment? Yes, I am. There we go.